Hi everyone and welcome to this new video tutorial. We're going to see right now some basic machine learning algorithm to recognize handwritten digits. We're going to start with the most simple one, but still really effective. And for example, we start with a sample of digits, which is this one. So we have approximately, I'm not sure, I think 250 of each number. So we have 250 zeros, 251, and so for each number until 9 for each digit. And we're going to pass this image to the algorithm, and starting from this sample data, then later we can use our test data. So we have few more numbers, this one for example, and we will see if the algorithm is able to recognize and say, hey, this is a 0, this is a 0, this is 1, 1, and so on for each digit. We will use the k nearest neighbor algorithm. If you don't know what it is, I will suggest you to see the other video tutorial that I've done about this. You can see in the link in the description, to at least learn how it works and the principle of the algorithm, and then you can follow this video. We're going right now to build it line by line in this video. So let's start. We import CV2, import numpy as np, and let's load the digits. So digits is equals to cv2.imRead digits.png, and we're going to load them in grayscale format. So cv2.imRead grayscale. Let's see if everything is correct. So we show them cv2.im show digits, and then digits, cv2.wait key 0, and finally cv2.destroy all windows. And after this, let's run this one, and we have them loaded correctly. And about this file, you can load also this file from the link in the description. After we have the digits, well, what about the digits? We have the digits all in just one image. So we need to divide this image in cells so that we take each single digit. We know that we have 250 digits, or better, let's say this way. We have 50 rows and 50 columns. So let's start splitting them. First we take the rows. It's equals to np vertical split v split. So this is a numpy function to split the array, so this digit array, and we're going to split it in 50 parts. So we split which one digits into 50 parts. So for example, if we show the first row, so row 0, let's copy this one, cv2.im show row 0, instead of digits will be row 0. We can see that here we have the first row. So now we have all the rows in this array. Now that we have 50 rows, we also want to split the row. So we have this one, we need to split it like still by 50. So it will be the cells, let's put it this way, cells, it's an empty array. So for row in rows. So now we're going to see each row one by one. We loop through the first one and we cut all them to the second one, all them, and we put all in the array of cells, so we will have all of them. For row in rows, we will have the cell, it's equals to, let's say, np.h split, in this case horizontal split, and we want to split the row in 50 parts. Once we split it. Actually, this is already cells. Actually, this will be again an array containing 50 cells, so it's not just one cell, it will be cells of also this one. I just want to give different name, not to confuse the two different arrays. Let's call it row cells. Let's call it this way. So we will have, for example, row cells 0. I'm just doing this just to show you, to understand it easier, but it's not necessary that you do this one. Row cell 0, and we break the loop just to show 1 to you, and I don't know where it is. mp.h row cells 0. Okay, it's not showing because I'm showing again on the same name, and somewhere I should have the number 0, and here it is. Now I have it on the other screen, number 0, and so on for that row. So now we loop also inside these row cells, so we get each single cell. So for cell in row cells, we can do this way: cells.append cell. So all this operation is to have all the numbers splitted. So now we will have, as we know, we have 50 by 50, so it's 2500 digits, and we will have all them organized this way. So cv2.im show cell, let's say we want to show the cell 250. So 250 will be this one, so from 0 to 249, so from 250 to 499, and so on. So if we display the last ones, it will be this 9, so 2499, and exactly is that 9 that I have right now on the other screen. You can see is this one. Okay, this operation just to have all the cells. Still there is a lot to go. Now we have all the cells, we can do something else. Let's do the same way for the test digits. So for this one we split, and we actually no. Yeah, let's do it. Test digits is equals to cv2.im read test digits.png, and also this one cv2.im read grayscale. Test digits, in this case it's easier, it's just one column, and it will be mp.h split the test digits into 50. So we will show if everything is correct. Let's show just the first one to see if we're doing it correct. And no, actually I did a mistake. It's v split, not h split, and I have it on the other screen, the 0, which is a total new 0 only for the test digits. So it's okay, we have both. we have the test digits and we have the digits to train. Right now we can already use the KN algorithm, so let's load it. KNN is equals to CV2.ml, which stands for machine learning, ml, and k nearest underscore create. Then we can train KNN equals to CV, no, what's CV2? Okay, let's stop it here for the moment. So we have the cells. We have 2,500 cells. Now we need to say to the algorithm, hey, this is a 0, this is a 0, this is a 0, this is 1, this is 1, this is 1, and so on, so that the algorithm can label correctly each one of these. We know that the first 250 are zeros. After that 251, then 250 number 2. So it's easy to do this with a numpy function, which will be, let's call it train labels, or better, let's say cells labels, as we are talking about cells labels. It's equals to np.repeat, we repeat the k, no, actually repeat k 250, and then we need to also use k equals np dot a range of 10. So really easy, we print k, so you can see what we are doing right now. This is simple, an array from 0 to 9, all the digits that we have. And we're going to repeat each one of these 250 times, and then we move to the next one. So that's why we use this array and repeat for 250. So it will be cells labels for seeing. Don't type this, I'm just showing you how it is. Print C and what? I think I did some mistake. Okay, not cells but cell labels. Exactly, we have each digit 250 times, so that we can label them correctly. So it will be KNN, it's equals to KNN dot train the cells and then cells labels. And you can see that we got an error. Type error, only size 1 arrays can be converted to Python scalars. Why? Well, the algorithm doesn't work with straight with the images, but works only with arrays. So for example, if an image is this way, let's print the cell, just print only one of them, and then we break. So here we are printing just one image. So this is the first row of the image. Actually, it will be this image, cv2.im show cell and cell. And I'm commenting it now because it gives an error. So for example, we are then this number 0, if I'm thinking that I'm printing that one in the moment, yeah, it corresponds exactly to this array that was printed. So first line, for example, is all 0, like all black, then like the second row, and it gives us this image. It gives us exactly that image, but the algorithm cannot work with multiple arrays, so we need to convert the image in one single array. So there is a NumPy function which is called flatten, and you will see now it works. Instead of putting the cell inside the cells, we're going to change the format. So cell, it will be equals to cell.flatten, and now I'm going to show you exactly how it changes. So this is the image of before, all in one line. This is our 0 that we used before, straight into one line. And that's it, how we're going to pass it. We don't need to show this, and now it should work. So kn.train, still it doesn't, because we need to do something else. Okay, we need to convert the cells. It's just a normal array, and you must be always aware that with OpenCV we need to always use NumPy array, because NumPy is faster than normal arrays, and we need speed when doing computer vision. So cells, it's equals to np.array cells, and the d type, it's equals to np.float 32. And this should be enough, I think. Oh, okay, there is also, I think, one more thing. Here in knn.train, between cells and cell labels, we need to pass this argument. Honestly don't know why they did this. c2.aml.rowSample. And that's all for the moment. So now we're already saying to the algorithm which number corresponds. So that this is, all these are zeros, or these are ones, and all these are two, and so on. Now it's the moment where we're going to test the algorithm if it works. So now we pass the digits. We're going to pass these digits, and is the algorithm which needs to tell us, hey, this is a 0, hey, this is a 0, and so for each digit. Let's see if it can guess correctly each single digit that we give him. And be aware that these are all new digits, so these digits that you find here are not here, of course, otherwise it would be like easy to guess. So they are still 0, but they are different. All of them are different, this one and also this one. So what now? Now that we have the test digits, I think that it should be enough. So it will be knn.find nearest of the test digits, and let's say k equals 1 for the moment, and later I will explain how exactly it works. We got an error, and I know why. Do you know why? The same thing that we did before to flatten the original cells of the train data, we need to do again now for the test digits. And we can do it in another way, or let's say test cells, so it will be easier. It's an empty array, and we do for test digits, for d in test digits, d it's equals to d dot flatten, and then test cells dot append d, and finally we convert this array into a numpy array. Test cells it's equals to test to np.array test cells, and d type it's equals to np.float32. Let's try this way. Still some error. No, I don't know what it is, to be honest. Let's see what we get. Okay, because I'm finding the nearest of test digits, but we're going to do of test cells, the new array that we just created, and k equals 1. Now everything works. We don't need to show the digits anymore, so we don't even need this one. And I was forgetting that this function gives us many things. It returns many things like ret, result, neighbors, and dist. And now we are only interested in the result. Print result. So if we take the image, this is the result of all the numbers. So if we take this one, not this one, but the one that I probably just closed, test digits, and we compare them with the result, so it says this one is a 0, and we see the first one is 0, second one 0. And as we know that we have 5 of each, 1, 2, 3, 4, 5 of each digits, let's see what we get. 0, 0, 0, 0, so to 5. All the ones are correct. The first number 2, it was misclassified, so we got 5 instead of 2. So the algorithm doesn't know that this is a 2, but thinks that this is a 5. All the other 2s are correct. All the 3s are correct. The 4's correct. 1, 5 was misclassified. Exactly the second 5. No. 3. The third 5 was misclassified. This one, it says it's number 1. Anyway, you got the idea. But now, one thing that I want to get into details, because I notice it's really hard to find the explanation online about how the algorithm works in this case. And I'm going to tell you that. In simple words, let's say that we have the digits. How can we train this one and then from this one detect the correct digits of this one? Well, the algorithm works this way. It takes the number 0 and take each one of them. So first it finds the distance between this 0 and this 1. So it's called Euclidean distance. If you want to know more about Euclidean distance, you can look it on Google or Wikipedia, but basically it takes the distance between this number and this number, and it gives us a result. For example, let's say 50. Of course, the less the distance, the more similar it is. And then again, it does this the same with the second number, and it calculates the distance and does this for each single digit. In this case, we have 2,500 digits, so it takes the distance with 2,500 of them. And this happens for each one. So we have 2,500 like calculation just for this first number, and the same for all of them. So what do you know from this? For sure we know that it's okay if we have small images, but not really good to use this with big images, because it takes huge computational power as it has to make each time all this calculation. And also for this, okay, I was saying this about the distance, and then it compares like the closest number using the KNN. For example, now we use only the closest distance, only one. Otherwise, if you want to use more distance, you can use 3. And you can see for you what's best for the algorithm. There is not an exact number of k to use. Sometimes a smaller k is better, sometimes a bigger k is better, but usually you can use around 3 or 5 or 7 or 9. But make sure always odd number. For example, let's try this with 3. It misclassified different things. Probably it's even worse than k equals 1. But anyway, also keep in mind that to use this algorithm, all the digits must have the exact same size. In this case, the size of each digit was 20 per 20, and also of the test digits. Keep in mind, using this method, always same size. If it's not clear, I will suggest you again to watch the video about KNN, the previous video I made about KNN algorithm, and practice with that. I hope that this video is clear. If you have any question, please put it in on the comment, and thanks for watching.